Force on a straight wire carrying a current in a constant magnetic field. We'll first deal with this and then discuss forces on two current carrying wires. This is established experimentally. So it is well known that the force on a current carrying wire for any angle between the wire and the constant magnetic field is given by the cross product. Force is IL cross B, where you can understand the cross product by using a particular right hand rule, which is shown here. So you have to stretch your three fingers on your right hand such that they are all perpendicular to each other. So the index finger stretches out and the middle finger is perpendicular to the index finger, and so is the thumb perpendicular to the index finger. So let's get that set up. Then what the cross product says is that if you move the vector A towards the vector B, that is, you move your index finger and make it parallel to the middle finger, then the resultant A cross B is given by the direction of the thumb. So this is also the direction in which a right-handed screw would turn. So if you turn the screw with a wrench from A to B, your screw would go up. So that's the version of right-hand rule we are using here. Now, of course, in this case, we have vectors instead of A, B, and C. The vector L, which is parallel to the current, and of course the magnetic field B, and F is the force. So L cross B will give you the force. In particular, what this rule states is that if the wire is parallel to the field, it will feel zero force, and if it's perpendicular to the field, it has the maximum force. In between, there is a factor sine theta that tells us what is the magnitude of the force. The direction of the force, of course, is always given by this right-hand rule. This definition of the force on a current carrying wire can also be used to fix the unit of the magnetic field. So if we have a wire carrying 1 amp of current in a and it experiences a force of 1 Newton, then we say that the magnetic field is 1 Tesla. Now let's talk about forces between two current carrying wires. So we have wire 1, which is carrying a current I1, and wire 2, which is carrying a current I2, and both the currents are in the same direction. Now we can apply another right-hand rule in order to figure out what is the sense in which the magnetic field is curling around each of these wires. So that's given by the dots and the crosses shown here for wire 1. So how did we get that? You can use, you curl the fingers of your right hand around the conductor and the direction of the thumb in the direction of the current, and the curling fingers will tell you the sense in which the magnetic fields are threading the wire. So this means that on the top here, the wire, the magnetic field is coming out of the board. That's the tip of the arrow. And then at the bottom of the wire here, the magnetic field is going into the board, which is the feathers on the arrow. So similarly for current I2, since it's in the same direction as I1. Now, let's ignore the top part of the figure and just consider at the bottom here without showing the magnetic field due to the current in wire 1. So we're going to ask, what is the effect of this current um, uh, felt by the current going in the conductor wire 2? So therefore, we show only the magnetic field arising from the current in wire 2, and we hide the magnetic field coming from here. So in order to find the force, we have to use that same expression, F equals IL cross B, except now the B that we have, the magnetic field, is being produced by the second wire. And in the proximity of wire 1, that magnetic field produced by the second wire is coming out of the board, shown by the dot, by the circle with the dot. So the expression F equals IL cross B suggests that the force on the wire 1 is downwards. So why is that? So we again apply the right-hand rule we discussed earlier. This is the other version of the right-hand rule. And the rule is that we have to put the index finger in the direction of the current, and the magnetic field here, which is coming out of the board, is represented by the middle finger, which is bent such that it's coming out of the board. And the magnetic field, the force then is given by the thumb, which is pointed downwards. So therefore the force on wire 1 due to the magnetic field by wire 2 is downwards. Forces are always equal and opposite, so therefore the force on wire 2 will be upwards. We can apply the same ideas to loops carrying current. So here is shown two single loops which are powered by a battery. The arrow indicates the direction of the current. Both of them are identical, both the loops are identical. The magnetic field, of course, is given by threading the the fingers of your right hand around the loop, and the thumb would point in the direction of north-south here, this way. So that would be the direction of the magnetic field. Since the south pole is looking at the north pole here, they would attract. So two loops carrying current in the same direction would attract. This is an important consequence, particularly for electromagnets and solenoids, which are extremely powerful. If it had been the other way around, there would be repulsive forces between the windings, and one would have had to invent a glue which is very, very strong to hold the magnet. But fortunately, the windings attract each other and they hold onto themselves by their own forces.